In the fall of 1959, on October 7th to be exact, something happened that forever changed how we think about the moon and started a new chapter in space exploration. The Soviet Automatic Interplanetary Station, Luna 3. The spacecraft, which embodied the most advanced engineering solutions of its time, performed an unprecedented maneuver. For the first time in history, it flew around the moon and looked at the hidden side, which had remained invisible until then. This breakthrough was equivalent to a blind person suddenly regaining their sight. Luna 3 was launched just 4 days before this momentous event, on October 4th, from the Baikonur Cosmodrome. Its mission was extremely complex and innovative. The spacecraft had to follow a complex ballistic trajectory that would allow it to circle the moon and enter a trajectory that would ensure communication with Earth during data transmission. The very idea of photographing the moon from such a distance and then transmitting the images was a huge challenge. There were no digital cameras on board the station in the modern sense. Instead, a highly inventive but cumbersome and complex mechanism was used, an optical camera that exposed standard photographic film. After shooting, the film was automatically developed, fixed, and dried right on board the spacecraft in a vacuum and weightless conditions. Truly, a heroic engineering solution. Then, the processed negatives, after passing through a complex optical scanning system, were converted into electrical signals that were transmitted to Earth via radio channel. This transmission process was painfully slow and prone to interference, and the quality of the first images left much to be desired. They were dim, grainy, and distorted in places, like blurred shadows of ancient artifacts. However, despite all the technical limitations, these images were invaluable. The world held its breath as it gazed at these first images, evidence that the cosmic curtain had been lifted. This was not just the acquisition of new information. It was a triumph of human intellect and engineering, a demonstration of the ability to comprehend what once seemed unattainable. The Soviet Union celebrated this victory as another important step in space exploration. And of course, it was a powerful blow to the ambitions of the United States, which was striving to be the first to reach the moon. Luna 3 not only showed that we could see the far side, but also paved the way for future, more ambitious missions. This event confirmed the words of the great scientist and thinker, Albert Einstein. It is important not to stop asking questions. Curiosity has its own reason for existing. Luna 3 was the embodiment of that curiosity, resulting in a remarkable technological achievement that made the whole world gasp and rethink our place in the universe. Now that the curtain had been lifted, humanity was eager to find out what was really hidden behind it. When the first, albeit blurry images from Luna 3 reached Earth and were decoded, the reaction in the scientific community was predictable. A mixture of surprise and, perhaps, slight disappointment among those who expected to see something sensational, something beyond the bounds of conventional understanding. However, for geologists and planetary scientists, it was a revelation. What we saw was completely unexpected and radically different from the familiar face of the moon that had hung above us for millennia, dotted with dark spots of seas and bright highlands. Instead of the expected vast seas, which, by the way, are frozen lava plains and not water basins, as ancient astronomers believed, covering most of the visible side of the moon, we saw an almost continuous field, scarred by countless craters. It was a landscape reminiscent of the weathered face of an old warrior bearing the scars of countless battles. Every answer begets new questions, says ancient wisdom, and the first images of the far side of the moon were a vivid confirmation of this. While the visible side of the moon is dominated by so-called lunar seas, vast, relatively smooth and dark lowlands formed by basalt lava eruptions after major impacts, surprisingly few such seas were found on the far side. About 30% of the visible side is covered by seas, while on the far side this figure did not exceed 2%, and the seas that were discovered turned out to be significantly smaller in area. Instead, the far side was a densely built-up landscape of thousands and thousands of craters, layered on top of each other like traces of hail that had passed through billions of years of the solar system's history. These craters ranged in size from giant basins stretching hundreds of kilometers to countless small pits. The scientific community immediately began analyzing this discovery. Initial hypotheses suggested that such a dramatic difference in landscapes indicated fundamental differences in the geological history of the two sides of the moon. It was suggested that this was due to differences in the thickness of the lunar crust. Later studies confirmed that the crust on the far side of the moon is significantly thicker, up to 100 kilometers in some places, which is almost twice the thickness of the crust on the visible side, which averages about 40–50 kilometers. This greater thickness of the crust probably made it difficult for magma to reach the surface after large impacts, preventing the formation of extensive lava plains. The volcanic activity that formed the seas on the visible side was suppressed on the far side. This fact raised many new questions. Why is the crust on the far side of the moon thicker? What were the conditions of its formation? Is this related to asymmetry in the distribution of the moon's mass, or to the peculiarities of its accretion in the early history of the solar system? Studying this crater-strewn landscape has opened up the possibility of looking back into a much more ancient era. Less volcanic activity means that the surface of the far side of the moon has preserved traces of billions of years of bombardment by cosmic bodies. It is a veritable time capsule, storing information about the early history of the solar system and the intensity of meteorite activity during that period. As the famous geologist and planetary scientist Eugene Shoemaker once said, "The Earth is a book written by nature, and the moon is another book written by space." And now, thanks to Luna 3, we have in our hands the first page of this second book, promising incredible stories and discoveries. These initial, seemingly dim images became the cornerstone for future, much more detailed studies, which we will discuss further. After the first, albeit very modest in quality, images of the far side of the moon became available to the scientific community, planetary scientists were presented with a landscape that was radically different from the familiar face of the moon. It was like suddenly discovering, after years of studying one side of a painting, that the other side depicts something completely different, created in a different style and conveying a different message. The main thing that caught the eye and continues to provoke deep study is the almost complete absence on the far side of the vast seas, those very dark, relatively smooth plains formed by solidified lava flows, which are so noticeable on the visible side and form its recognizable contours. If the visible side of the moon is associated with a kind of lunar horizon, where flat lowlands give way to highlands, the far side is something else entirely, like a huge titanium shield, pockmarked with countless scars from cosmic impacts, having absorbed the full force of meteorite bombardment. The landscape of the far side of the moon is dominated by vast ancient highlands known as terrae, which occupy a smaller area on the visible side. These areas are extremely densely cratered territories, where one crater overlaps another, creating a complex topography that bears witness to billions of years of cosmic history. The average surface elevation on the far side is significantly higher than on the visible side, which is dotted with seas. The difference in altitude between some areas can reach several kilometers. Imagine a geological landscape where there are virtually no plains, but instead endless chains of mountains formed by the ridges of ancient giant impact basins, dotted with younger craters like pockmarks on the face of an ancient giant. Each crater on this side of the moon is a kind of wound inflicted from outside, but at the same time, a time capsule storing information about the moment of collision. The number of craters per unit area on the far side exceeds their density on the visible side many times over. This is not only a visual, but also a structural difference. Geological maps of the far side look like abstract patterns, where every curve and every circle is the result of a catastrophic event that left an indelible mark. The sizes of these craters vary from a few meters to hundreds or even thousands of kilometers in diameter, with depths that can reach several kilometers. Many of them have central peaks, which are the result of rock rebound after impact, as well as ray systems extending hundreds or even thousands of kilometers from the epicenter. This clear difference in morphology, less smooth and more rugged, makes us think about the dynamic processes that shaped the moon over its 4 billion years of existence. While the visible side of the moon shows relatively extensive areas of volcanic activity where magma poured onto the surface, filling impact basins and creating vast plains, the far side of the moon does not appear to have been affected by this process to the same extent. It is as if one side of a giant celestial body was protected from the outpourings of internal heat, while the other erupted with fountains of molten rock. Understanding these differences is the key to unraveling the mystery of the moon's symmetry, which, as we shall see, is much deeper than it seems at first glance. It is not just a question of surface, but of the structure and evolution of the entire celestial body. The main reason for the striking absence of extensive seas on the far side of the moon, in contrast to its near counterpart, lies in a fundamental geological difference that has been confirmed by numerous orbital missions and gravitational field analyses: the thickness of the lunar crust. Scientists believe that the crust on the far side of the moon is significantly thicker, while on the visible side, the average thickness of the crust is approximately 30 to 50 kilometers. On the far side, it can reach 60 kilometers, and in some areas even up to 100 kilometers. This circumstance, like a solid barrier, made it difficult for magma to erupt from the moon's interior to the surface, which led to the formation of a significantly smaller number of extensive seas. Imagine the moon's mantle as a giant reservoir of molten rock. On the visible side, where the crust is thinner, magma could relatively easily break through to the surface through cracks formed after large impacts, filling these impact basins and forming the very seas that we see with the naked eye. On the far side, however, the more massive and thicker crust acted as a kind of armor, significantly increasing the resistance to upward magma flows. Even the most powerful impact events that could have created basins large enough for magma to fill them encountered an insurmountable obstacle in the form of this thickened lithosphere. It is similar to how water that can easily seep through a thin sand dune would be stopped by a thick granite rock. The question of why the moon's crust is asymmetrical in thickness remains one of the most intriguing and actively debated in planetary science. There are several competing theories, each attempting to provide the most complete explanation for this phenomenon. The theory of asymmetric accretionary growth. According to this hypothesis, in the early period of the moon's formation, when it was still young, hot, and plastic, the accretion of matter could have occurred unevenly. Perhaps the gravitational influence of the Earth, which was at a close distance, caused more material to settle on the side farther from the Earth, leading to the formation of a thicker crust. Theory of tidal influence and differentiation. The Earth's tidal forces could have played a key role in the early, still molten state of the moon. These forces could have caused the lighter silicate rocks floating on the surface of the magmatic ocean, which form the crust, to shift away from the Earth. This is similar to how oil and water will tend to collect in a certain place under the influence of external forces. Multiple impact theory. Some scientists suggest that the asymmetry of the crust may be the result of early, very large impacts. Perhaps a series of giant collisions on the visible side of the moon led to the thinning of its crust, while the far side remained relatively untouched by these colossal events, retaining its original, thicker structure. The well-known South Pole Aitken basin on the far side, which will be discussed in detail in the next chapter, is one of the most striking examples of this type of event. Unraveling this asymmetry has profound implications for our understanding of the formation and evolution of the moon as a whole. It allows us to build more accurate models of its internal structure, thermal regime, and volcanic history. It is as if, while studying the anatomy of a creature, we discovered that one half of it developed completely differently from the other. Why does the moon, our closest neighbor, exhibit such bipolarity? This question is driving scientists to conduct new research and develop more sophisticated probes and missions capable of shedding light on this fundamental mystery. As Carl Sagan said, "We are the way the universe knows itself." And studying the asymmetry of the moon is one of the ways in which space is trying to understand its own seemingly incomprehensible laws. While the visible side of the moon, thanks to extensive lava flows, is a relatively young surface where ancient craters have been hidden under layers of basalt, the far side is a veritable time capsule. Less volcanic activity, and consequently, the absence of large-scale surface renewal means that this part of the moon has preserved traces of billions of years of cosmic bombardment, allowing us to glimpse the earliest and most turbulent stages of the solar system's history. It is similar to how archaeologists, excavating untouched layers of soil, can reconstruct a picture of long-lost civilizations. The far side of the moon is our cosmic archaeological site. where every crater is a chronicle, every mountain range a witness to ancient cataclysms. Scientists use a method called crater counting to date the surfaces of celestial bodies. The more craters per unit area, the older the surface, as it has been bombarded for longer. In this respect, the far side of the Moon is an ideal textbook. Its densely cratered highlands provide invaluable information about the so-called late heavy bombardment, a period believed to have occurred approximately 3.8 to 4 billion years ago. At that time, after most of the planets had formed, the solar system was subjected to a significant increase in the number of comets and asteroids, which intensively bombarded the inner planets, including Earth and the Moon. On Earth, most traces of this bombardment have been erased by geological processes such as plate tectonics and erosion. But the Moon, being geologically much less active, has preserved this cosmic archive. The surface of the far side of the Moon is living testimony to the intensity and distribution of impact events in the early solar system. By analyzing the sizes and distributions of craters, scientists can reconstruct the history of the asteroid and comet populations, understand how they evolved, and how their orbits changed over time. This is critical to understanding the processes of planet formation and the emergence of life. After all, it was these early bombardments, although destructive, that may have also brought water and organic molecules to Earth, which were necessary for the emergence of life. Thus, the scars on the far side of the Moon can tell us about our own earthly origins. In addition, the absence of volcanic activity over large areas of the far side means that lunar soil samples collected there may be much more pristine and contain information about the earliest composition of the Moon, unaltered by later magma outflows. This makes it an ideal location for future sample return missions, which could provide invaluable data to test existing models of the formation of the solar system. It's like finding an ancient, unopened library filled with manuscripts written at the dawn of time. Every particle of regolith, every fragment of rock on the far side of the Moon could be a piece of the puzzle that could unlock secrets rooted in the depths of cosmic history. As Carl Sagan said, "If you want to bake an apple pie from scratch, you must first invent the universe." By studying these ancient surfaces, we are essentially trying to understand how our own universe was baked and what place we ourselves occupy in it. This is not just astronomy. It is profound philosophy embodied in stone and dust, waiting for its explorer. When it comes to the geological features of the far side of the Moon, it is impossible to ignore one of the most striking objects not only on the Moon, but in the entire inner solar system, the South Pole Aitken Basin. This is not just a crater, it is a colossal scar carved into the body of our natural satellite billions of years ago, a witness to the most ancient and grandiose cosmic catastrophe. Its diameter is about 2,500 kilometers, stretching from the south pole of the Moon to the Aitken crater, which gave it part of its name. The depth of this giant reaches an astonishing 13 kilometers at some of its deepest points, making it one of the deepest known depressions on the surface of any solid celestial body in the solar system. It is not just a giant structure, it is an anomaly that is still the subject of intense study and a source of many scientific questions. It is believed that the South Pole Aitken Basin was formed as a result of a collision with an asteroid or comet several hundred kilometers in size at the dawn of the Moon, possibly during the so-called late heavy bombardment period, approximately 4 billion years ago. The force of this impact was so tremendous that it pierced a significant portion of the lunar crust, exposing, as scientists believe, deeper layers of the Moon's mantle. This makes the South Pole Aitken Basin a unique window into the interior of our satellite, providing a rare opportunity to study the composition of its subsurface layers without the need for drilling to great depths. Studies of the composition of the South Pole Aitken Basin floor using orbital spacecraft have revealed elevated levels of elements such as iron and titanium, which may indicate the presence of mantle material. This is critically important for understanding the differentiation processes of the Moon, how light elements rose to the surface to form the crust, while heavier ones sank to the center to form the mantle and, possibly, the core. Each new satellite flying over this basin, each spectral analysis of its surface, brings new data that allows us to refine hypotheses about the internal structure of the Moon and its thermal evolution. It's as if we had the opportunity to take an X-ray of the entire planet. In addition, The South Pole Aitken Basin is located in the area of the Moon's south pole, which means that part of its bottom is in the zone of so-called permanently shadowed craters. These areas are never exposed to direct sunlight, creating conditions for the preservation of volatile substances, such as water ice, which could have been delivered to the Moon by comets or asteroids. This gives the South Pole Aitken Basin a dual significance. On the one hand, it is a geological time capsule, and on the other, it is a potential treasure trove of valuable resources for future manned missions. Studying this giant scar is not just academic curiosity, it is a path to uncovering the fundamental mysteries of planetary formation and securing humanity's future in space. Great discoveries begin with great questions, as an eminent scientist would say. The South Pole Aitken Basin poses many great questions for us. While Earth has a powerful global magnetic field generated by convection in its liquid outer core, the Moon today is essentially devoid of such a field. However, orbital studies of the Moon, which began with the Apollo missions and continued with more modern probes, have uncovered one of the most intriguing mysteries of its geological past: strange localized magnetic anomalies that are particularly pronounced on the far side. These anomalies are areas of residual magnetization, similar to how a piece of iron retains its magnetic properties after being exposed to a strong magnetic field. The most famous example of this phenomenon is the so-called Reinnergam anomaly, located in the ocean of storms on the visible side of the Moon. But it is on the far side that such manifestations are much more frequent and stronger. These findings provide convincing evidence that the Moon once had a global magnetic field similar to Earth's. This field must have been generated by an internal dynamo effect, i.e., the movement of conductive material in its core, which at that time must have been liquid and possessed sufficient thermal energy for convection. The existence of such a field in the distant past of the Moon, presumably about 4,200,000,000 to 3,200,000,000 years ago, raises a number of fundamental questions. Why did this field disappear? What caused it to arise, and why did it not survive to the present day, as it did on Earth? There are several scientific hypotheses that attempt to explain the origin and subsequent extinction of the ancient lunar dynamo. The theory of convective dynamo in a liquid core. The most common hypothesis suggests that in the early period of its history, the Moon had a sufficiently hot and possibly partially liquid core, where convective flows of molten metal could generate a magnetic field. However, over time, as the core cooled and solidified, this process ceased. The question is why the Moon cooled much faster than Earth, losing its dynamo. The theory of large impacts. Some researchers suggest that giant impacts, such as the one that created the South Pole Aitken Basin, could have temporarily restarted or intensified the dynamo's activity by transferring energy to the Moon's interior. However, this theory has not yet been widely confirmed. Mantle overturn theory. Another hypothesis suggests that the early Moon underwent a so-called mantle overturn, where denser material sank toward the center and less dense material rose. This process could have been powerful enough to temporarily cause movement in the core and generate a magnetic field. These magnetic anomalies are not just interesting local features, they are a kind of fossilized remnant of the Moon's ancient magnetic field. By studying their distribution and intensity, scientists can reconstruct the strength and configuration of this field in the past. This is extremely important for understanding how planetary bodies lose their internal energy, how their cores cool, and how their magnetic fields evolve. In addition, the presence of a magnetic field in the early period may have played a role in protecting the young Moon from harmful solar radiation, which could have been important for processes related to the potential emergence of life, if it ever existed on the Moon. "The past is prologue," said William Shakespeare, and in the case of the Moon's magnetic anomalies, its distant past sheds light on its present and future. Perhaps one of the most exciting mysteries discovered on the Moon in recent decades is the question of the presence of water ice at its poles, including on the far side. For a long time, the Moon was considered a completely dry, waterless body, which made it extremely inhospitable to any form of life or long-term human habitation. However, data obtained from a number of spacecraft, such as Lunar Prospector, Chandra-1, and later L-Cross, Lunar Crater Observation and Sensing Satellite, radically changed this view, opening up a whole new perspective for future lunar expansion. The essence of the discovery is that signs of water ice have been found in deep craters at both lunar poles, especially those located in the so-called permanently shadowed regions, PSRs. These areas are never illuminated by direct sunlight due to the low angle of sunlight at the poles and the deep shadows cast by the crater walls. Temperatures in these cold traps can drop to extremely low values, approaching absolute zero, down to -230 degrees Celsius, which is ideal for preserving water ice in the lunar vacuum. Evidence of the existence of water has accumulated gradually. First, there was data from the Lunar Prospector's neutron spectrometer, which detected elevated hydrogen levels in the polar regions, which could be an indicator of water ice. Then, in 2009, the L-Cross experiment, which deliberately directed the upper stage of a launch vehicle into the Beats crater near the South Pole, recorded the ejection of a column of material, analysis of which confirmed the presence of significant amounts of water as well as other volatile substances. Subsequent studies using radars and spectrometers from other spacecraft, such as the Lunar Reconnaissance Orbiter and India's Chandrayaan-1, confirmed the presence of water ice, although not in its pure form, but most likely mixed with lunar regolith, a surface layer of dust and rocks. This discovery is of enormous importance for future lunar missions and long-term human presence on the Moon. Water is a key resource for sustaining life. It can be used for drinking, for obtaining oxygen for breathing through electrolysis, and for producing rocket fuel, hydrogen and oxygen. Thus, water on the Moon is transforming from a purely scientific interest into a strategically important resource that could significantly reduce the cost and complexity of future space expeditions. If there is no need to deliver water from Earth, which is extremely expensive, then the possibility of establishing permanent bases or even mining minerals on the Moon becomes much more realistic. However, despite the optimism, there are still a number of important questions that need to be answered. How much ice is there? What is its concentration in the regolith? How easy is it to extract and process in the lunar environment, given the extremely low temperatures and complex terrain of permanently shadowed craters? These questions are central to the planning of future missions, such as the US Artemis program and the Chinese Chang'e program, which are specifically targeting the polar regions. Water is life, as the famous saying goes. And on the Moon, it could be the key to opening a new chapter in human history, transforming our dry and seemingly barren satellite into a potential outpost for humanity in deep space. However, this is still more of a hope than a certainty, and unraveling its true volume and accessibility is one of the main tasks of modern planetary science. After humanity finally overcame centuries-old limitations and peered beyond the mysterious edge of the Moon, it would seem that the era of speculation should have ended, giving way to empirical knowledge. However, contrary to rational expectations, this invisible side, having shed the mask of absolute obscurity, only plunged deeper into the mythological abyss, becoming fertile ground for a wide variety of often fantastical conspiracy theories. The paradox is that it was precisely partial knowledge, an incomplete picture, reinforced by centuries-old prejudices and psychological patterns, that raised even more questions than it answered. From secret alien bases hidden in craters and hidden valleys, to secret military programs of earthly powers, allegedly conducted in complete ignorance of the public, these myths have spread like weeds on the fertile soil of human imagination and mistrust, feeding the minds of millions and turning scientific facts into the subject of endless debate. The psychological background to this phenomenon is quite profound. Human beings are, by their very nature, creatures who seek meaning and order in the world around them. When confronted with something as grandiose and mysterious as the far side of the Moon, hidden from view for billions of years, our brains strive to fill the information vacuum. Even if this happens through the creation of incredible narratives, the unknown is frightening, and for many, the idea of secret powerful forces, whether aliens or hidden government structures, hiding something is less disturbing than the realization of the colossal amount of the unknown. In addition, humanity has a certain archetypal idea of forbidden knowledge that is supposedly withheld from the masses by the elite. This idea, rooted in myths and legends since time immemorial, finds its perfect embodiment in conspiracy theories about the Moon. Examples of such cultural myths are numerous and varied. One of the most popular is the claim that ancient or active alien bases exist on the far side of the moon. Proponents of this theory often refer to supposedly strange structures seen in photographs of the lunar surface, ranging from monoliths to towers and domes, which, in their opinion, may be of artificial origin. These objects are usually optical illusions, plays of light and shadow, or simply natural geological formations that the human brain, prone to pareidolia, the perception of familiar images in random stimuli, interprets as something meaningful. Nevertheless, the belief that they are already here, simply watching us while remaining invisible behind the lunar horizon, persists, reinforced by thousands of videos on internet platforms and books filled with pseudoscientific evidence. In addition to alien bases, there are other equally fascinating myths. During the Cold War, when the space race was an arena for ideological confrontation, theories arose about secret military programs on the moon. For example, Project Horizon, a real, albeit long since declassified and unrealized plan by the U.S. Army to establish a military base on the moon in the 1950s, became fertile ground for the development of conspiracy theories about allegedly already built and operational secret lunar outposts. Some researchers claim that both superpowers secretly created joint or separate bases where certain experiments are conducted or Earth is monitored, and all information about this is carefully hidden from the world community. This idea is fueled by a general distrust of government structures and a belief that there is always something going on behind the scenes that ordinary people do not know about. The cultural roots of these myths run deep. They reflect our fears of powers we do not understand or control, whether they be alien civilizations or powerful earthly governments. They serve as a kind of safety valve for anxieties about future technological progress and our place in the universe. Renowned astronomer and science popularizer Carl Sagan, who often spoke out against pseudoscience, emphasized the importance of critical thinking. Extraordinary claims require extraordinary evidence. However, for many, belief in conspiracy is more appealing than the complexity and uncertainty of scientific reality. These myths, passed down by word of mouth from generation to generation, have become part of modern folklore, demonstrating not only the power of the human imagination, but also its tendency to self-deception in search of simple answers to complex questions. They do not just tell us about the moon, they tell us about ourselves, about our need for mystery and our ability to create it, even when reality offers much more prosaic but no less surprising explanations. In the boundless ocean of conspiracy theories related to the far side of the moon, stories about lost missions, unexplained signals, and crashed spacecraft occupy a special place. These stories, like cosmic mirages, constantly circulate in the depths of the internet and marginal publications, feeding the imagination of millions and generating endless debates about the hidden truth. The essence of these claims boils down to the fact that the government and space agencies, primarily NASA, are deliberately hiding sensational discoveries made on the far side of the moon from the public, whether they be traces of extraterrestrial life, evidence of advanced civilizations, or evidence of catastrophic events. Of course, scientific data and thousands of hours of observations from orbital spacecraft and telescopes do not confirm these claims, but their very existence only emphasizes the profound mystery and appeal of this region to the human mind. One of the most common and persistent claims is the story of lost missions that allegedly successfully reached the far side of the moon, but information about them was classified. For example, there is a myth about a secret Soviet mission that allegedly discovered something remarkable on the far side, but all the data was destroyed or hidden because of the inconvenient nature of the discovery. Similarly, conspiracy theorists claim that some of the Apollo missions, not those that landed on the visible side, actually flew around or even made secret landings on the far side, making contact with alien civilizations or discovering ancient artifacts. The evidence often cited consists of blurry photographs that supposedly show strange objects, or testimonies from former NASA employees, whose names usually remain unnamed or turn out to be fictitious. Another category of evidence is related to unexplained phenomena. These can be reports of mysterious radio signals allegedly coming from the far side of the moon, or unusual lights and moving objects recorded by amateur astronomers or on satellite images. These phenomena usually have a very prosaic explanation. They may be radio interference, optical illusions caused by the play of light and shadow on the lunar surface, or even just dust particles on the telescope lens. The phenomenon of pareidolia, which we mentioned earlier, plays a key role here. The human brain tends to see familiar shapes in random patterns, whether it's a face on Mars or a giant base on the moon. Nevertheless, for conspiracy theorists, these random coincidences or natural phenomena become irrefutable evidence of a hidden truth. The existence of these myths, despite the lack of any scientific confirmation, is an important indicator not only of human curiosity, but also of our tendency to distrust. In an age when information spreads at the speed of light and the authenticity of sources is often questioned, conspiracy theories find fertile ground. The irony is that often scientific data, such as detailed maps of the lunar surface obtained by modern orbital spacecraft with a resolution of tens of centimeters, which demonstrate the absence of any artificial structures, are used by conspiracy theorists as evidence that someone is hiding something, since incomprehensible shadows or landscape features can be interpreted in any way. As Carl Sagan said, "Where there is no data, there is no knowledge, only speculation." And in the case of the far side of the moon, speculation thrives where there is no immediate, complete, and absolutely clear answer. These myths, while pseudoscientific, undoubtedly underscore the deep, almost mystical appeal of the moon's unseen side. They remind us that even in an age of space travel and incredible scientific discoveries, the human mind continues to search beyond the horizon for something more than just rocks and dust, even if that something more is a product of its own imagination. The real mystery of the far side of the moon is not that it hides aliens, but its unique geological history, its asymmetry, and the scientific secrets it still holds, secrets far more complex and amazing than any fictional story. After the stunning breakthrough that gave humanity its first glimpse of the hidden face of the moon, one might have expected scientific enthusiasm to intensify, paving the way for continuous exploration. However, contrary to this expectation, interest in the far side of the moon seemed to wane over many decades. The reasons for this retreat were multifaceted, but one of the most fundamental and insurmountable was the technological difficulties associated with maintaining communication and navigation with spacecraft on its invisible side. This problem is not simply an engineering challenge, but a consequence of the immutable laws of physics, which the moon, due to its size and position, uses as a natural screen. The main problem, like an invisible barrier separating our world from what lies beyond the horizon, is communication. Radio waves, which are the primary means of transmitting data and commands between Earth and spacecraft, travel in a straight line. The moon, being a massive celestial body with a diameter of about 3,474 kilometers, simply blocks these signals. Imagine trying to call a friend on the other side of the Earth, but there is a huge, impenetrable obstacle between you. Similarly, a device on the far side of the moon is literally in a radio shadow. Direct radio communication with Earth becomes impossible. This circumstance, of course, was not a discovery after the first flights. Scientists and engineers knew about it in advance, but its practical consequences turned out to be extremely serious. In order to maintain continuous communication with the spacecraft on the far side, an additional element is required: a relay satellite, which must be in orbit around the moon and act as an intermediary, receiving signals from Earth and transmitting them to the spacecraft, and then sending the data back. Building and launching such a relay satellite is a complex and expensive mission in itself. It requires a separate launch vehicle, additional time for development, production, and testing, as well as complex control and positioning in orbit. Such a satellite must be equipped with powerful antennas capable of receiving weak signals from Earth and the surface of the moon, as well as having enough energy to transmit them. All this significantly increases the complexity, risks, and importantly, the financial costs of any mission to the far side. It's as if, for every phone call, you first had to build a special communication tower halfway between the two parties. In addition to communication, navigation is an equally difficult task. Without direct visibility from Earth, ground tracking stations cannot directly determine the exact position and speed of a spacecraft on the far side of the moon. This means that the spacecraft must rely on autonomous navigation systems, such as inertial navigation systems, INS, and use onboard sensors, star sensors, and cameras for spatial orientation. more accurate gravitational models of the moon are needed to predict its impact on the spacecraft's trajectory. In the early space age, when computer systems were much less powerful and sensors less accurate, such autonomous navigation was a serious challenge. Any error in calculations or equipment failure could result in the loss of the spacecraft. It was like sailing in uncharted waters without a compass or starry sky, relying only on intuition and rough maps. An example of such difficulties is the Luna 3 mission itself, which, despite its triumph, encountered enormous difficulties in transmitting data due to limited radio communication. In subsequent years, when space agencies were faced with the choice between simpler and cheaper missions to the visible side of the moon or other planets and much more complex and expensive projects to the far side, the choice was often made in favor of the former. These technological limitations essentially erected an invisible wall around the far side of the moon, making it less accessible and, as a result, less of a priority for exploration in the post-moon race era. They became one of the key reasons why this unique region remained relatively unexplored for many decades, awaiting new technological solutions and changes in strategic priorities. The peak of the space race in the 1960s and early 1970s became a symbol of unprecedented national prestige and technological power for the United States and the Soviet Union. The Apollo missions, especially the landing of a man on the moon in 1969, were not just scientific expeditions. They were monumental demonstrations of engineering capabilities and political will. However, after this grand goal was achieved, interest in the moon, and especially its difficult-to-explore far side, began to decline steadily. This decline was due to a combination of economic reasons and a fundamental shift in space policy priorities. The space race, although it brought many technological innovations, was an extremely costly undertaking. The Apollo program, for example, cost the United States the equivalent of more than $280 billion in today's dollars. Such huge financial investments were only possible in the context of a unique geopolitical confrontation, when the struggle for space was perceived as a critically important part of national interests and ideological leadership. With the end of the active phase of the Cold War and the U.S. victory in the lunar race, this powerful incentive for unprecedented spending on space weakened. Public attention shifted to other, more pressing problems on Earth, and the political will to fund costly lunar missions waned. Along with the changing political landscape, scientific priorities also changed. In the 1980s and 1990s, space agencies shifted their focus to exploring other planets in the solar system. Mars, with its potential for discovering traces of ancient life, the mysterious gas giants Jupiter and Saturn with their multitude of moons, and distant worlds that could reveal the formation of the entire planetary system became new magnets for scientific curiosity and investment. The launch of space telescopes such as Hubble ushered in a new era of astronomy, allowing us to peer into the farthest corners of the universe. Compared to these exciting prospects, relatively modest and, as it then seemed, already understood lunar research, especially complex missions, such as those to the far side of the moon, came to be seen as less of a priority, or, as some officials put it, a luxury, rather than a necessity. Money is the nerve of war, said Cicero, and in the space race, it was the nerve of progress. The reduction in space budgets in the post-lunar era meant that every financial decision had to be as effective as possible. Missions to the far side of the moon, as we have already discussed, required significantly higher costs due to the need for relay satellites and complex navigation systems. This created what is known as an opportunity cost. Every dollar spent on a complex mission to the far side could not be spent on simpler or scientifically fruitful missions to other objects. In addition, the lack of immediate sensational discoveries on the far side of the moon after the first images also contributed to a decline in interest. The public, spoiled by the dramatic events of the space race, expected something more from the moon than just craters and mountains. When these expectations were not met, funding began to decline. Many believed that the moon had already been explored and that there was no point in spending huge resources on further study, especially of its invisible side. This misconception, based on incomplete information, only became more entrenched in the public consciousness. Thus, a combination of economic factors, changing political priorities, and a shift from the race to new, more distant scientific goals led to the far side of the moon being sidelined in the space program for decades. It became a reminder that even the most ambitious human aspirations are subject to changing circumstances and financial constraints. However, this neglect was only temporary, as we shall see below. After all, the fundamental scientific questions raised by the far side of the moon had not gone away, but were simply waiting for their moment to return to the spotlight. Although the problem of radiation in outer space affects the entire moon and any journey beyond the protective layer of the Earth's atmosphere and magnetosphere, it is worth mentioning that the far side of our satellite is, in a sense, in a slightly more vulnerable position. This circumstance, although not the main reason for abandoning its exploration in the past, certainly added complexity and risk to already difficult missions, reinforcing the general perception of its inhospitability. The space outside Earth's magnetosphere is not a vacuum, but an environment permeated by high-energy particles known as cosmic rays. The main sources of this radiation are solar proton events, bursts of high-energy protons and other particles ejected by the Sun during powerful solar flares and coronal mass ejections. These events are unpredictable and can be extremely dangerous, causing radiation storms that can seriously damage spacecraft electronics and pose a deadly threat to unprotected astronauts. Galactic cosmic rays are a more stable but continuous stream of high-energy particles coming from beyond the solar system, presumably from the remnants of supernova stars. They consist of the nuclei of atoms of various elements moving at nearly the speed of light and have enormous penetrating power. The Earth, like a loving mother, provides its inhabitants with relatively reliable protection from most of this radiation. Our atmosphere absorbs most of the galactic cosmic rays, GCRs, and solar proton events, SPEs, while a powerful magnetic field deflects charged particles, creating a kind of shield around the planet, the magnetosphere. The Moon, on the other hand, has neither a dense atmosphere nor a significant magnetic field. This means that its surface, whether visible or hidden, is constantly bombarded by these high-energy particles. However, in the context of the differences between the two sides of the Moon, one nuance should be noted. As the Moon orbits the Earth, its visible side periodically enters the shadow of the Earth's magnetosphere, which provides at least partial protection from solar flares and some GCRs. This is not absolute protection, but it does reduce the overall radiation dose. The far side of the Moon is always turned away from Earth and therefore never receives this partial but useful protection. It is in constant contact with interplanetary space, completely exposed to both solar and galactic cosmic rays. It is as if one side of a ship were periodically sheltered from a storm, while the other were always exposed to its full force. For spacecraft, and even more so for humans, radiation is a serious problem. High-energy particles can cause malfunctions in electronics, known as single-event upsets, accumulate charge in components, and ultimately disable equipment. For astronauts, prolonged exposure to high radiation levels increases the risk of cancer, central nervous system disorders, cataracts, and other serious health problems. Developing effective radiation protection methods is one of the key challenges for future missions to the Moon, especially for establishing permanent bases. Thick layers of regolith or special shielding materials are required, which in turn increase the mass and complexity of the structure. Thus, although the problem of radiation is universal for the Moon, the far side of the Moon, which does not even benefit from the partial shadow of the Earth's magnetosphere, is a slightly more challenging environment for long-term stays and work. This factor, along with the aforementioned communication and navigation difficulties, as well as economic considerations, contributed to the exploration of the far side of the Moon, taking a back seat after the first pioneering missions. It became a reminder of the harsh reality of outer space, where every advantage, even the smallest, can be crucial to the success of a mission and human safety. However, as we will see below, new technological advances and changing priorities are poised to challenge these dangers once again, ushering in a new era of lunar exploration. After decades of relative obscurity, when the Moon seemed to take a back seat in space priorities, giving way to more distant planets, the far side of our natural satellite has once again taken center stage. This return to the origins of space exploration was marked by a monumental achievement that rewrote the history of space exploration. In 2019, the People's Republic of China made a historic breakthrough by successfully landing its Chang'e 4 automatic probe and Yutu-2 rover on the surface of the far side of the Moon. This event was a first in human history, marking not only a technological triumph, but also a powerful geopolitical statement about China's rise as a leading space power. The Chang'e 4 mission was launched in December 2018, and a month later, January 3, 2019, the landing module gently descended into the von Kármán crater, located within the giant South Pole Aitken basin, the largest and oldest impact crater on the Moon, which we discussed earlier. This was not just a successful launch, it was a carefully planned and flawlessly executed undertaking that overcame enormous technological barriers. The main one, of course, was the problem of communication. As we have already discussed in detail, direct radio communication with the far side of the Moon is impossible due to the Moon's body blocking the signal. Chinese engineers solved this problem by launching the Queqiao relay satellite in May 2018, which was placed in a halo orbit at the Earth-Moon Lagrange point. This unique orbit allows Queqiao to constantly see both the Earth and the far side of the Moon, acting as a space bridge for data transmission. It was an engineering solution worthy of the highest praise, demonstrating not only a deep understanding of orbital mechanics, but also the courage to implement innovative ideas. The Chang'e 4 lander and Yutu-2 rover were equipped with a suite of advanced scientific instruments designed to conduct comprehensive investigations of the surface and subsurface layers of the far side of the Moon. These included a low-frequency radio spectrometer designed to conduct radio astronomical observations free from terrestrial interference. This was one of the key scientific experiments, as the far side of the Moon is an ideal place to listen to the universe in the radio band, free from billions of interferences generated on Earth. A panoramic camera and a topography camera for detailed study of the landscape, a lunar penetrating radar, LPR, to study the subsurface structure of the regolith and detect hidden layers, and even a neutral atom detector to study the interaction of solar wind with the lunar surface. Yutu-2 became the first planetary rover in history to begin its research on the invisible side. Its journey, which lasted much longer than planned, allowed it to collect invaluable data. The scientific results obtained by Chang'e 4 and Yutu-2 began to reveal new secrets of the far side. Detailed images of its cratered surface were obtained. The composition of the regolith was analyzed, confirming the uniqueness of this region. Radar studies by the rover revealed the presence of subsurface layers, which may indicate the complex geological history of the formation of the South Pole Aitken basin and the characteristics of magma effusions, which were significantly less frequent here than on the visible side. Moreover, data from the low-frequency radio spectrometer, although requiring lengthy analysis, promised to be a breakthrough in radio astronomy, allowing scientists to look into the dark ages of the universe, the period before the formation of the first stars, when space was filled only with neutral hydrogen. This experiment opens up completely new horizons for understanding the earliest stages of the universe's evolution. The success of the Chang'e 4 mission was not just a technical achievement, it was a turning point in global space policy. Not only did it cement China's status as a full-fledged player in the space race, but it also served as a powerful catalyst for other space powers, forcing them to rethink their strategies and turn their eyes back to the Moon. This event, like a cosmic shot, awakened the Moon fever of the new century, proving that even decades after Apollo, the Moon continues to hold many unsolved mysteries, and its exploration is not only a scientific, but also a strategic priority. Humanity will not remain on Earth forever, predicted Konstantin Tsiolkovsky, and the Chang'e 4 mission has become yet another confirmation of this statement, pointing the way to new, unprecedented achievements in space exploration. The success of China's Chang'e 4 mission to the far side of the Moon served as a powerful catalyst, inspiring other countries and private companies to turn their attention back to our natural satellite with an enthusiasm unseen since the Apollo era. This event, like a trigger, launched a new lunar race. But this time, it has taken on the character not only of competition, but also, and more importantly, of international cooperation and partnership. Plans for the coming decades include a series of ambitious missions that promise to reveal even more secrets of the far side, pave the way for the delivery of valuable soil samples, build advanced observatories, and ultimately establish permanent bases. One of the most significant projects prompted by this new wave of interest is NASA's Artemis program, which aims to return humans to the moon, not just for short-term visits, but to establish a sustainable presence and then prepare for a mission to Mars. A significant part of this program is focused on the moon's south pole, which, as we have already discussed, is the site of a potential accumulation of water ice in permanently shadowed craters. Many of these craters are located on the far side of the moon or near its polar regions. The Artemis program involves a series of missions, including both robotic landings to explore resources and technologies and manned flights, culminating in the landing of astronauts. The plan is to use new rovers capable of operating in the extreme conditions of the polar regions, collecting ice and soil samples and conducting experiments on their processing. In addition to Artemis, a number of other space agencies and countries are actively developing their own lunar programs. China is continuing its ambitious Chang'e program with plans for the Chang'e 6 mission, which will aim to deliver soil samples from the far side of the moon to Earth. This would be another historic breakthrough, allowing scientists to study samples of the oldest lunar crust, which has not been affected by later volcanic activity. The European Space Agency, ESA, is also planning missions to the moon, including in collaboration with NASA as part of the Artemis program, and is developing concepts for its own rovers and scientific instruments. The Japan Aerospace Exploration Agency, JAXA, and the Indian Space Research Organization, ISRO, are also taking an active interest in the polar regions of the moon, developing their own missions. Radio astronomy is the most important scientific field for future missions to the far side of the moon. As we have already mentioned, the far side is an ideal location for low-frequency radio telescopes, as it is completely shielded from electromagnetic interference generated on Earth, radio, television, mobile communications, the internet, etc. This allows astronomers to listen to the faintest and most ancient signals from space, including those relating to the dark ages of the universe, a period when the first stars and galaxies had not yet formed. The construction of such an observatory on the moon would be a revolution in astronomy, comparable to the advent of the Hubble telescope, only at a completely different frequency level and with a signal frequency inaccessible from Earth. The prospect of building permanent bases on the moon, including on its far side, is no longer the stuff of science fiction novels, but has become a real goal. Such bases could serve as scientific outposts, places for the extraction and processing of resources, primarily water ice, as well as training grounds for further manned missions into deep space. Concepts are being developed for living modules capable of withstanding extreme temperatures and radiation, life support systems based on the use of local resources, and autonomous robotic systems for construction and maintenance. The future depends on what you do today, said Mahatma Gandhi. And in the context of lunar exploration, this means that every new achievement, every successful launch, brings us closer to establishing a permanent human presence beyond Earth. The far side of the moon, once mysterious and inaccessible, is now seen as a strategically important frontier where scientific ambitions intertwine with economic opportunities and global aspirations. This is not simply a return to our roots. It is a step forward that promises to reveal the most intimate secrets of our cosmic neighbor and open new horizons for all of humanity. The history of space exploration, especially in its early days, was primarily a story of rivalry and competition between two superpowers. However, as space programs developed and the enormous costs and technological challenges became apparent, it became clear that the most ambitious projects in space, such as the exploration of the moon, and even more so its far side, required joint efforts. The study of the far side of the moon, with its unique scientific mysteries and strategic potential, is becoming a powerful point of contact for international cooperation, bringing together scientists, engineers, and governments from around the world in an effort to unravel its secrets. Historically, international cooperation in space has already proven its effectiveness with the International Space Station, ISS, a grand engineering and political achievement that has served as an example of successful cooperation between different countries for decades. The principles underlying the ISS, sharing costs and risks, exchanging experience and technology, and jointly using scientific results, are becoming the basis for new lunar programs. No country, even the most powerful, has all the necessary resources and expertise to independently and comprehensively explore the moon and establish a presence there. Cooperation allows us to combine the best of each country, scientific minds, engineering talent, and financial capabilities to achieve common goals that sometimes seem unattainable. An example of such cooperation is NASA's Artemis program, which actively invites partners from around the world to participate. The European Space Agency, ESA, the Japan Aerospace Exploration Agency, JAXA, the Canadian Space Agency, CSA, and other countries have already joined the initiative, providing their modules, technologies, and astronauts for future missions. These partnerships may include the development of common standards for equipment, the creation of joint training programs, and the exchange of scientific data and analytical tools. For example, ESA and JAXA plan to provide their modules for the Gateway Lunar Orbiting Station, which will serve as a staging point for missions to the lunar surface. Why is such cooperation so important for exploring the far side of the moon? In addition to the economic benefits, it allows us to overcome the technological difficulties that have long hindered its study. The development and deployment of relay satellites, the creation of robust communication and navigation systems, the development of rovers capable of operating in extreme conditions, and of course, the design and construction of habitable bases. All these tasks require enormous effort and a wide range of expertise. By sharing these tasks among several countries, progress can be accelerated and the individual burden reduced. Moreover, international cooperation in space has a profound philosophical significance. It demonstrates that humanity, despite all its earthly differences, is capable of uniting for the common goal of knowledge. As Carl Sagan said, space is something that exists within us. We are made of stardust. We are space's way of knowing itself. And exploring the far side of the moon, the hidden face of our celestial neighbor, is precisely such a way of knowing. It reminds us that, despite all our political boundaries and cultural differences, we are part of one big cosmic family, and our most ambitious achievements can only be realized through unity and shared aspirations. Of course, international cooperation in space is not without its challenges. These include political complexities, differences in technical standards and legislation, as well as issues of intellectual property and the equitable distribution of resources. However, the benefits it brings, accelerating scientific discoveries, reducing costs, strengthening international relations, and demonstrating humanity's ability to undertake ambitious joint projects, far outweigh these difficulties. The exploration of the far side of the moon, once considered a luxury, is now becoming a symbol of a new era of space exploration, where common goals and mutual benefits unite nations, paving the way for unprecedented discoveries and possibly a permanent human presence on the moon and beyond. After delving into the depths of history and modern research on the far side of the moon, the question arises about its future. And that future may be determined not only by scientific curiosity, but also by pragmatic economic interests. The far side of the moon, with its unique geology, ancient history, and relative isolation from Earth's influences, may hold not only invaluable scientific data, but also significant economic treasures. There are well-founded assumptions about the presence of rare minerals and other valuable resources there, which, provided that the appropriate technologies are developed, could become not just a help, but a real driving force for the future lunar and then extraterrestrial economy. The concept of lunar resources has long ceased to be a fantasy. Regolith, the surface layer of lunar dust and debris, is a valuable resource in itself. It can be used to extract oxygen, which makes up about 45% of the regolith's mass, and is necessary for breathing and fuel production, as well as metals such as iron, titanium, and aluminum, which can be used to build lunar bases and spacecraft. However, the far side of the moon may offer something more specific and valuable than just ubiquitous elements. Its unique geological history, characterized by a significantly thicker crust and fewer volcanic eruptions, means that its surface may have preserved more ancient and possibly more concentrated deposits of certain minerals. Many researchers are focusing on helium-3, a light isotope of helium that is a potential fuel for future fusion reactors. Fusion using helium-3 is considered a clean energy source because it produces no radioactive waste and emits no greenhouse gases. Helium-3 is found in extremely small quantities on Earth, but there is much more of it on the Moon. It accumulates in lunar regolith as a result of bombardment of the surface by solar wind, which has carried these atoms from the Sun for billions of years. Although helium-3 is present throughout the Moon, its concentration can vary depending on the composition of the regolith and its age. Theoretically, only about 1 gram of helium-3 can be extracted from 100 tons of lunar regolith, but given its energy value, this still makes it an extremely attractive resource. Research shows that the South Pole Aitken basin, with its ancient surface and deep regolith, may contain elevated concentrations of this isotope. However, its extraction requires enormous energy costs and complex technology involving heating huge volumes of regolith to hundreds of degrees Celsius. In addition to helium-3, scientists also suggest the possibility of other rare and valuable elements on the far side of the Moon. Given that the far side is less prone to volcanic activity and has an older and thicker crust, it may have preserved more materials related to the earliest stages of the Moon's formation. These could be unique isotopes, rare Earth elements that are important in high-tech industries on Earth, as well as platinum metals. Some giant impact basins, such as South Pole Aitken, may have exposed or brought to the surface rocks rich in these elements that might not be accessible on the visible side of the Moon. However, these assumptions remain largely theoretical models and require confirmation through detailed geological studies and sample analysis. The economic feasibility of lunar mining certainly remains a subject of intense debate. The high cost of delivering equipment to the Moon, the extremely harsh environmental conditions requiring robotic systems that are resistant to radiation and extreme temperatures, and the enormous energy costs of mining and processing resources make this process extremely difficult. Nevertheless, as Earth's reserves are depleted and space technology advances, the prospects for lunar mining may become increasingly attractive. This could usher in a new era in human history, an era of space economy, where resources extracted from beyond Earth will be used both to sustain activities and to meet the growing needs of our planet. As rocket pioneer Robert Goddard once said, "It is difficult to say what is impossible, because yesterday's dream is today's hope and tomorrow's reality, and lunar resources may well become that reality." When it comes to the Moon and life, most scientists agree that the probability of discovering indigenous life originating on the Moon is negligible, practically zero. The lack of atmosphere, liquid water on the surface, extreme temperature fluctuations from plus 120 degrees Celsius during the day to minus 170 degrees Celsius at night, as well as high levels of cosmic radiation make the Moon extremely inhospitable to the forms of life we know. Nevertheless, contrary to this seemingly obvious hopelessness, the far side of the Moon takes on a unique significance in the context of biological research, but in a completely different way. It could become an ideal clean room for searching for extraterrestrial life in samples brought back from other planets, or for studying the reaction of Earth microbes to extreme space conditions. The uniqueness of the far side of the Moon lies in its biological isolation from Earth. Our planet is a teeming hotbed of microorganisms that are constantly being ejected into space by spacecraft, even the most sterile ones. This phenomenon, known as forward contamination, is a serious problem for planetary protection. When spacecraft contaminated with Earth microbes land on other celestial bodies, such as Mars or Europa, there is a risk that these microbes could survive, multiply, and possibly even distort the results of the search for local life. The far side of the Moon, being permanently shielded from Earth by the Moon itself, is much less susceptible to this form of contamination. Its atmosphere, if it exists at all, is extremely thin, and it is not directly exposed to microbes carried by Earth winds or random space debris. This makes the far side of the Moon an ideal location for future facilities to analyze samples returned from other planets. If, for example, a mission returns samples from Mars, where there is the potential for microbial life to be found, analyzing them in a lunar clean room minimizes the risk of false positives due to Earth contamination. It also provides a double layer of protection for Earth. If the samples happen to contain unknown, potentially dangerous extraterrestrial microbes, they can be safely studied and, if necessary, quarantined on the Moon without putting Earth's biosphere at risk. This concept of biological isolation is a cornerstone of planetary protection strategy, which aims to prevent both the contamination of other worlds by Earth organisms and the return of potentially dangerous extraterrestrial organisms to Earth. In addition, the far side of the moon could become a unique laboratory for studying extremophiles, Earth microorganisms capable of surviving in the harshest conditions. Conducting controlled experiments with Earth microbes in conditions of low temperatures, deep vacuum, high radiation, and constant shadow on the far side of the moon will allow scientists to better understand the limits of life's survivability and its adaptive capabilities. This research is crucial for understanding where life may exist in the solar system and beyond, as well as for developing strategies to protect astronauts and equipment from microbiological threats during long space flights. This is similar to how doctors study the response of organisms to disease in sterile conditions in order to develop medicines. Philosophical and ethical aspects are also important. If we ever discover traces of life on Mars or another celestial body, the far side of the moon could become a place to study it, where maximum protection from contamination would be ensured. This will raise questions about our responsibility as a species capable of influencing the biological environment of other planets, our duty to protect potentially existing extraterrestrial life, and our obligations toward our own planet. As the famous astrobiologist Carl Sagan said, understanding that life is a rare and precious phenomenon should serve as a lesson in humility for us. And the far side of the moon, thanks to its biological isolation, offers us a unique opportunity for this understanding, providing a kind of research reserve that can shed light on the greatest questions of life's existence in the universe. Despite decades of research, thousands of photographs, and tons of data analyzed, the far side of the moon continues to be a source of profound mysteries and probably still harbors many unknown phenomena that have yet to be discovered. Each new piece of information obtained from orbital spacecraft and rovers not only provides answers, but also inevitably raises new, more complex questions, forcing us to constantly rethink our understanding of this celestial body. What if its unique geology hides completely new, unpredictable forms of lunar activity that are not visible on the visible side, or even relics of the distant past of the solar system that we do not even suspect yet? Science, by its very nature, is an endless process of discovery. The deeper we delve into the mysteries of the universe, the more clearly we realize the extent of our ignorance. The far side of the moon, with its ancient, densely cratered surface that has not been renewed by extensive volcanic eruptions like the visible side, is a veritable cosmic museum, where each exhibit is a testament to events long past. It is quite possible that deep beneath its surface, hidden from our current observation methods, there are unique mineral deposits or crystalline structures that could have been formed as a result of ancient colossal impacts that penetrated the mantle, or during processes that are no longer active on the visible side. The discovery of such unknown minerals could not only revolutionize our understanding of lunar geology, but also offer new technologies or resources for use. Perhaps there are also unknown geological processes. Although the moon is considered geologically dead compared to Earth, some forms of activity may persist. For example, could there have been some kind of cryovolcanism associated with potential reserves of volatile substances deep below the surface, which manifested itself or manifests itself in a different way due to the characteristics of the thick crust on the far side? Or perhaps there are unique forms of seismic activity, so-called moonquakes, that differ in nature from those observed on the visible side, and that could indicate unusual movements in the moon's interior. We still do not have a complete picture of its internal structure, and every anomaly, whether magnetic or gravitational, serves only as a hint that processes we do not yet know about may be taking place in its interior. We should not discount unknown unknowns, phenomena whose existence we do not even suspect, because they go beyond our current scientific paradigms. Remember how, decades ago, no one even suspected the existence of water on the moon, and then it turned out to be a revolutionary discovery. Or how gravitational anomalies called mascons were only discovered after the first orbital vehicles began to experience unexpected changes in their orbits. What if, in the depths of the South Pole Aitken basin, this colossal scar, there is hidden evidence of the earliest stages of the formation of the solar system? Perhaps even fragments of planetesimals that collided with the moon but have not undergone significant changes over time. Studying the far side of the moon in this way is not just a process of filling in gaps in our knowledge, it is an adventure into the unknown. It is a constant expansion of our understanding of how the planets were formed, how the solar system evolved, and what place our own planet and life occupy in it. As Albert Einstein said, the most beautiful thing we can experience is the mysterious. It is the source of all true art and science. And the far side of the moon, with all its mystery and potential for unexpected discoveries, remains one of the most mysterious and attractive objects in our solar system, promising to be a source of scientific wonder for many generations of researchers. Its secrets are waiting to be revealed, and each new study brings us closer to a more complete understanding of this amazing celestial body. The far side of the moon, once shrouded in mystery and remaining only an object of speculative conjecture, is now transforming from a simple subject of scientific curiosity into something much more fundamental, a key stepping stone, a springboard for humanity's future missions into deep space. It is not just an object of study, it is a strategically important outpost that could become a starting point for ambitious journeys to Mars, the asteroid belt, and possibly even beyond our solar system. This concept, rooted in early dreams of interplanetary travel, is now taking shape thanks to advances in rocket science, robotics, and technologies for utilizing local resources. The advantages of launching spacecraft from the moon compared to Earth are numerous and extremely significant. First, there is significantly lower gravity. Lunar gravity is only about 1/6 that of Earth, which means that significantly less energy and, accordingly, less fuel is required to launch a payload into orbit. This represents a tremendous saving in resources and costs. Imagine trying to climb a high mountain while carrying a heavy load. It is much easier to start climbing from a gentler slope with less gravitational pull. For missions to Mars or more distant corners of the solar system, every kilogram of fuel that is not needed to overcome Earth's gravity becomes a valuable asset that can be replaced with scientific equipment or additional supplies. Secondly, the vacuum environment of the moon is ideal for assembling and launching spacecraft. The absence of an atmosphere means there is no aerodynamic drag or adverse weather conditions. This allows for lighter and less robust rocket designs, which on Earth would have to be much more massive to withstand atmospheric pressure during launch. In addition, in a vacuum, there are no problems with condensation, corrosion, and other atmospheric effects, which simplifies equipment maintenance. Thirdly, and perhaps most revolutionary, is the availability of resources on the moon itself. In particular, water ice found in permanently shaded craters at the poles, including those on the far side, is an invaluable asset. Water can be electrolyzed to produce hydrogen and oxygen, the components of rocket fuel. Thus, the moon could become a giant refueling station in space, where spacecraft bound for Mars or beyond could fill their tanks without relying on costly fuel deliveries from Earth. In addition, lunar regolith contains oxygen, about 45% by mass, as well as metals such as aluminum, iron, and titanium, which can be used for 3D printing and building infrastructure on the moon, such as living quarters, launch pads, or protective structures. This embodies the concept of in situ resource utilization, which is key to long-term space expansion. Specifically, the far side of the moon offers additional unique advantages for its role as a stepping stone. Its relative radio isolation from Earth, which we discussed as a challenge for communications, could be a blessing for certain types of activities. For example, sensitive radio astronomy observatories could be located here, free from terrestrial interference, allowing them to listen to the universe undistorted. Perhaps it is from the far side of the moon that the first signals from extraterrestrial civilizations, if they exist, will be transmitted. This isolation also makes it an ideal place to launch spacecraft that must not be exposed to terrestrial radio emissions, for example, to search for traces of life or signals from distant stars. Creating such a stepping stone in space requires significant infrastructure. This includes the development of habitable bases for crews, life support systems capable of operating in a closed cycle, automated resource extraction and processing systems, and a lunar orbital station, such as Gateway, which will serve as a transit point between Earth, the Moon, and deep space. These are huge investments in the future, but they promise dividends that could transform human civilization. The transition from rare, costly expeditions to a sustainable presence and use of lunar resources. This is not just a change in tactics, it is a fundamental change in our place in the universe. The transformation of humanity into a truly interplanetary species. As Konstantin Tsiolkovsky said, "The planet is the cradle of reason, but one cannot live in a cradle forever." The moon, and especially its far side, is our first step out of that cradle, paving the way to the stars. The exploration of the moon, and especially its hidden side, which for centuries has remained a symbol of the unknown and untouched, presents humanity not only with grandiose engineering and scientific challenges, but also with profound philosophical and ethical questions. These questions touch on the very essence of our existence, our responsibility to future generations, to the moon itself as a unique celestial body, and to potential extraterrestrial life. As the moon ceases to be merely an object of observation and becomes a potential territory for exploitation and permanent habitation, we will have to develop new rules and principles to regulate this new chapter in human history. One of the central issues is governance. Who will own the moon's resources? How will control over its territory be exercised? The existing Treaty on Principles, governing the activities of states in the exploration and use of outer space, including the moon and other celestial bodies, the Outer Space Treaty of 1967, prohibits the national appropriation of outer space. However, it does not provide clear guidance on commercial activities or resource extraction. This gives rise to the so-called tragedy of the commons, a situation in which individual users, acting in their own interests, deplete a shared resource, even if this is contrary to the long-term interests of all. Recent initiatives, such as the Artemis Accords, developed by the United States and a number of other countries, attempt to create a framework for regulating lunar activities, but their provisions remain subject to debate and criticism, especially from countries that are not participating in them. How can humanity, which often faces conflicts over resources on Earth, ensure the fair and peaceful exploration of the moon? Another important ethical aspect is planetary protection. A permanent human presence on the moon increases the risk of both forward contamination, the transfer of Earth microorganisms to the moon, and backward contamination, the potential return of unknown and possibly dangerous extraterrestrial microbes to Earth. Although the probability of life existing on the moon is extremely low, and we are striving for biological isolation on the far side, the risk of contaminating other celestial bodies, such as Mars, via lunar bases, still exists. How can we ensure that our quest for exploration does not lead to irreversible changes in the unique geological or, possibly, even biological environments of other worlds? The responsibility for protecting these pristine corners of the universe lies with us, and every decision about landing, drilling, or building must be made with these ethical imperatives in mind. Questions also arise about extraterrestrial heritage. Should the sites of the first landings on the moon, such as the Apollo or Chang'e 4 landing sites, be protected as cultural and historical heritage of humanity? What criteria should be used to identify such sites? How can their preservation be ensured in the context of future commercial activity or construction? These questions raise the issue of the balance between progress and preservation, between aspirations for the future and respect for the past. Finally, the exploration of the moon raises fundamental questions about our place in the universe and our future as a species. Will we become a multi-planetary species? How will this affect our culture, our self-awareness, and our relationship with Earth? Will lunar settlements develop as independent societies, or will they always be connected to Earth? These questions may sound like science fiction, but as the moon becomes more accessible, they cease to be purely speculative and require serious philosophical consideration. As the famous thinker and writer Arthur C. Clarke said, "The natural way to discover the limits of the possible is to go beyond them into the impossible." But with this opportunity comes responsibility. We must not only reach for the stars, but do so consciously, with wisdom and a deep understanding of the ethical implications of our actions. The journey to the far side of the moon that we have undertaken in the pages of this book, from ancient myths and the first blurry photographs to the most modern robotic missions and ambitious plans for the future, is only a brief stop on a much longer and more exciting journey. The far side of the moon, once a symbol of the unattainable, mysterious, and invisible, has now become a symbol of a new era of space exploration, proof of humanity's unquenchable desire to understand and explore the universe. Its mysteries are not a barrier, but a powerful incentive for future generations of scientists, engineers, and researchers. We have seen how the moon, our closest celestial neighbor, holds the chronicle of the early solar system, how its geological asymmetry continues to pose fundamental questions about its formation. We have explored its unique features, from the colossal South Pole Aitken basin, which is a window into its mantle, to the mysterious magnetic anomalies that testify to a long-extinct magnetic field, to the potentially enormous reserves of water ice at the poles, which could be the key to a permanent human presence. We also encountered cultural myths and conspiracy theories that mirror our own fears and aspirations, but we were convinced of the inconsistency of their evidence in the face of rigorous scientific data. The return to active exploration of the moon, especially its far side after decades of neglect, is driven not only by technological advances such as relay satellites, but also by a profound rethinking of our place in space. The moon is no longer just a distant object of observation, but is becoming a potential outpost, an eighth continent for humanity. From here, with its low gravity and accessible resources, missions to Mars and beyond, to the mysterious worlds beyond the solar system, can be launched. It is no longer a question of whether we can do it, but how quickly we can do it and how we will manage it. Science, by its very nature, is a process in which every answer begets 10 new questions. The study of the far side of the moon is no exception. Every soil sample, every photograph, every signal received from its surface opens up new horizons for research. Perhaps deep beneath its surface lie new forms of minerals that we do not yet know about. Perhaps the analysis of ancient regolith will allow us to understand the processes that took place in the universe at the dawn of its existence. Perhaps it is on its quiet, isolated side that we will one day place radio telescopes capable of picking up the faintest echoes of the universe, or even signals from extraterrestrial civilizations. As the great science fiction writer and popularizer of science Isaac Asimov wrote, the most exciting phrase one can hear in science is not "Eureka," but "That's strange," and the moon, especially its far side, will undoubtedly continue to present us with many such oddities. Ultimately, the exploration of the far side of the moon is not just a project, it is part of humanity's endless journey to understand itself and its place in the universe. This desire, rooted in our nature, pushes us to overcome boundaries, to seek new knowledge, and to expand our presence beyond our home planet. The moon, once just a silver disk in the night sky, a symbol of mystery and romance, now appears before us in all its complex, multifaceted reality, as an ancient archive, as a future home, and as a springboard to the stars. And its far side, once invisible and incomprehensible, has become one of the most exciting symbols of humanity's endless, tireless pursuit of the horizon, beyond which new discoveries always await. As Robert Frost famously said, "Two roads diverged in a wood, and I took the one less traveled by, and that has made all the difference." The far side of the moon is such a road, one we are only beginning to explore, and it will undoubtedly change our future forever. M.